Welcome back, everybody, to the latest in our series of distinguished alumni colloquium speakers celebrating our 100th anniversary as a department. Today's speaker is Ben Montet. Ben was an undergraduate at Illinois, got his BS in physics and astronomy in 2011. He was another one of our Wyatt Award winners. He went on to Caltech to get his PhD with John Johnson. And after that, he was a Sagan Fellow at the University of Chicago. And since 2019, he's been a lecturer and Scientia Fellow at the University of New South Wales. Ben works on flares and low mass stars and exoplanets. And today he's going to tell us about stellar activity in the time domain. So go ahead.
Yeah, wonderful. Thank you for the introduction. It's really exciting to be here. Going back to my alma mater to give a colloquium was a real bucket list item here. So this is really fun for me. Like I said, unfortunately, can't be there in person to see you all and go to the Blind Pig afterwards, but we'll take what we can get here. We think of time domain astronomy as this hip new thing, right? This is in vogue right now. It's a buzzword. You look at the job register. There's all sorts of jobs in time domain astronomy right now. But this is not a new game. Time domain astronomy goes back to the invention of the telescope. Some of the first things we think of is Galileo looking at the moons of Jupiter and seeing how they change from night to night. Time domain astronomy is 500 years old. And stellar activity in the time domain is also one of the second things that Galileo looked at was the sun. I'm not advancing, there we go. And there's wonderful records from as far back as 1611, the pretty pictures go only to 1625, of observations of stellar activity in the time domain. This is a recording over a month in April or May 1625 of a starspot group moving across the sun from left to right over here, and a few different starspots. And so we have recordings of how the sky, how the sun is changing, going back almost 500 years, which provides a really, really nice baseline. And one of the things that this has been useful for is understanding long variations on the sun. We have comparisons to 500 years ago, but there's also a long history of planet searches informing us about stellar astrophysics. This is something that we think about now, but it goes back at least 200 years. We know the story of Neptune's discovery, the predictions from Leverrier as to where a planet might be because of perturbations on Uranus's orbits. But around the same time, there were also predictions of a planet interior to Mercury, because Mercury had this anomalous precession that we now know as the general relativity prediction at 43 arcseconds per century. But in the mid-1800s, there were very confident predictions of where the planet interior to Mercury would be that would cause this precession. It was called Planet Vulcan. It felt as real as Neptune would be, especially once Neptune was discovered. Confident enough for this map maker to put it on to the map of the solar system. It has a distance from the sun, so it has an orbital period. It was effectively a predicted planet. And so this led to planet searches to try to find this planet and characterize it in detail. And one clever astronomer, Heinrich Schwabe, looked at the predictions of where it would be and realized this planet would transit the sun. And so he started a transit monitoring campaign to see where can he detect the planet Vulcan, and observed the sun pretty regularly for 20 years looking for these transits. Along the way, he saw a lot of starspots, sunspots, and started making detailed records of how many sunspots there were over time, and noticed something interesting, which is that the starspots changed in number over time. There wasn't a regular amount of spots, but there's this increase and decrease over about 10 years. And so he published this in 1844, and it was the first evidence of the 11-year solar cycle, the magnetic activity cycle. He called it about 10 years, but what's a year between friends? And so this is the first real evidence for a planet search informing stellar physics, which is the game that we've continued to play for the past 200 years, really increasing in the past 25 years. And so even though we think of time domain astronomy and planet searches, and we learn about stars, know thy star, know thy planet, all these phrases as a fairly modern thing, this is an old story. The story has changed quite a bit recently. In 2009, there were two main developments that enabled me to be here giving this talk today. The first was the launch of the Kepler telescope in March of 2009. And the second, in January of 2009, I transferred from the School of Aerospace Engineering to the Department of Physics and the Department of Astronomy at U of I, and started working with Charles Gammy on a project on black holes. And along the way, got to do a couple other projects, work with Robert Brunner quite a bit on quasar variability, time domain project right there. Was lucky enough to go spend a summer at the NRAO in Charlottesville. There's young me. It's a really fun group. There's 3 people on this page are now faculty, 2 are postdocs, 2 have permanent positions at NASA centers. It was a really, really fun and inspiring group to work with. Then I eventually graduated from U of I. So it was a great time, really, informed a lot of what I have done for the past decade. And all that time, Kepler was still taking data. Kepler was a very regular clock, taking data every 30 minutes for 4 years on about 200,000 stars. And so why does it do that? Well, its goal was primarily to be a planet detection mission, looking for planets around other stars. And it is doing this through the photometric transit method, waiting for distant stars to have planets. When they do, occasionally there is some statistical chance these planets will be aligned just right so that they pass between us and the star. They cast their shadow on the surface of the star. And so if we can observe the brightness of the star, we see the shadow coming and going. And so then the size of the amount of starlight that's occulted, how much fainter the star gets, tells you about the relative size of the planet and the star. And the spacing between these dips tells you about the orbital period of the planet. You see one event every planet year. So that's planet transits in a nutshell. To motivate this spacecraft, how you would build it, there's 3 factors here. The first is that transits are pretty rare. That we need this geometric alignment to be just right for the Earth. Sun distance 1 AU. The probability of just any random system having the right alignment to see a transit is about 1 part in 200. So for if every system had an Earth-sized planet at 1 AU, you'd have to look at 200 to see one transiting. So this means we need to observe many stars to find a few transiting planets. So then Kepler looks at a pretty big field of view, something about as big as your hand at arm's length. Field looks like this. There's about 4.5 million stars in the field, of which 200,000 were targeted at 30-minute cadence. And so data from roughly 200,000 stars. The second issue is that transits are infrequent. As I said, you only really get information once per planet year. So for the Earth-Sun system, again, you get 1 transit every 365 days. It lasts about 13 hours. So you need to catch that. So you need continuous monitoring, and you need it at a fairly high cadence. So regular observations, Kepler went for every 30 minutes for most stars, every 1 minute for a few stars. And also transits are small. Earth is small relative to the sun. So if you're talking about the amount of area that's blocked, it's a pretty small effect. There's a black dot here you might or might not see. This is the actual relative size of the Earth to the sun. You might also have not seen this blue pixel down here, which is the relative size or relative area of the Earth to the whole slide being the sun. Those are the relative sizes of the dips you see. And so If you didn't notice either of those or both of those when the slide came up, that's probably a sign that, it's a small effect that you don't see unless you're looking very carefully for it. And so, this is about 80 parts per million for the Earth. So we need extremely precise instruments, and we also need to understand starspots. And so Kepler was launched in 2009, was a 4-year mission, observed every 30 minutes. It's something like on the order of 100,000 data points, 90,000 for 200,000 different stars. And then TESS is the follow-on mission, launched in 2018. Smaller telescopes, but observes larger regions of the sky. It's a region about 25 degrees by 100 degrees. This kind of rectangular sector of the sky, and over a year steps across different patches of the sky to observe the entire hemisphere, 1 month at a time. And because it's a square detector on a hemispherical sky, these squares overlap at the poles. And so at the ecliptic poles, you get a year of data. So these are kind of summary statistics. There's no exam at the end. Just I'll have it on a recording if you want to think about them later. But these are kind of remarkable numbers here. 1 million stars, 200,000 stars, 10 part per million photometry. These are things that are really, really useful for stellar astrophysics. They're designed for planets, but there's a lot of other games you can play with this data. Something like half of all papers, and it's 53% of all the papers from Kepler and TESS are on exoplanets, and 47% are not. So, even though they're designed as planet search missions, they're just as useful for other parts of astronomy. And so that's one of the things we'll talk about today is, how do we use this data to better understand stars? And so one of the ways we go about that is looking at kind of particular stars that we know might be active to understand how activity changes over time. And one of the places that is fairly common to go is to young stars. TESS has observed thousands of stars with known ages in young moving groups. So fairly precise ages too, better than 10-ish% age uncertainties. Across the whole sky. There are stars ranging from the very youngest star forming regions, upper SCO and places like that that are on the order of 10 million years old, down to the Hyades at 750 million years old. But so thousands of stars across the sky, nice distribution of temperatures, more or less following the IMF, with a slight magnitude limit at the faint end, and fairly bright, 10th magnitude on average. These stars are active. These are with lots of flares, lots of star spots. So there are exoplanets in here that people characterize in detail. These are both observations of systems with exoplanets. But it's not as obvious as you might think because they're buried under star spots and flare signals. You can see on the top panel here, 4% or so peak-to-peak variations from spots. You see big flares going on. Same deal here on the bottom, about 4% again. The top one is easy to see the planets because they're highlighted, but they're not necessarily obvious if you're just looking. And this is one planet. There's actually 3 other planets in the system that are harder to find. But it's very easy to see the activity signals. And so this is a real opportunity to understand both spots and flares and how they change as a function of time and mass and other parameters. And so one of the questions we want to understand is what do the surfaces of these young stars look like? How do they change? When do they change? How much do they calm down over time? And how can this affect things like habitability? So we know that stars calm down over time. Young stars, I just got a dog, and so I have to give this is not her, but I have to give metaphors that are dog related now as part of the contract. But stars are kind of like puppies. Young stars are very active. They're so excited they just burst everywhere. She's housebroken, but they have all sorts of energy that they give off. And as they get older, they calm down and just kind of hang out and watch the world go by. Stars are very similar, but in a more dangerous way. because young stars have all sorts of high energy emission, which can then strip a planet's atmosphere and turn your nice habitable planet with a thick atmosphere into a barren rock. And once you lose your atmosphere, it's harder to get it back and retain life. So we really want to understand the evolution of activity from a habitability standpoint.
Ben, I think we have a question. Brian, did you?
Yeah. So Ben, love the dog analogy, but a couple slides earlier on the sky map, I was just, forgive me, it looks like one of the quadrants is underpopulated. Is there a story there?
There's a boring story there, which is that this is from a paper we wrote, and at the time TESS hadn't finished the northern hemisphere.
Oh, okay.
And so this is the data that we had at the time, which was all of the south and half of the north. Got it.
Okay. But TESS isn't avoiding that. Yeah.
TESS is avoiding the ecliptic plane.
Right. Sure.
In order to, which is not the galactic plane, but the ecliptic plane, in order to maximize the regions that are kind of overlapping to get a year of data. And they avoided one small section here because of just an unfortunate way that the moon and the sun were arranged. Meant that it was going to get a lot of scattered light that would cause part of the detector to saturate. And so they shifted things a little bit, but there's no reason that these fields are being avoided.
Yep, got it. Cool. Thanks.
Yep. Cool. You get to see the dog again. It's cute. So one of the main questions then is how regular are flares? How much do they change over time? But then how do we find flares? Historically, this is done through heuristics. We look for certain cuts on certain numbers of outliers that are continuous, some sigma cut, and then inspect them by eye. Which is fine when you have a small number of stars, but with TESS we have 25 million stars observed over the 2-year mission, and so we don't necessarily want to look at all of them by eye. And also the heuristics sometimes leave some information on the table. It's very simple cuts that are done, which is sensible for big flares. That if you want 5 straight points, 5 sigma above the mean or something. Which is something like what this canonical paper from 2015 does a nice job catching on the big flares, but misses some of the little flares. 4 good ones here, but one small flare missing. And in the face of increased spot variability, more just noise in the long-term baseline of the data, these small flares get missed even more. But we know that flares have fairly characteristic shapes in many cases. They're this so-called Fred profile of a fast rise and an exponential decay. And so that's not leveraged in a lot of these simple heuristics. But we know that flares kind of look broadly to first order similar across all flares. And so this is an opportunity for machine learning, some sort of unsupervised learning methods. Because we have a model of what these should look like. We can train some sort of classifier on this is a flare, this is not a flare, and then let it loose on the test data. So this is a project that I have worked on with Adina Feinstein, a PhD student at the University of Chicago. Started when I was a postdoc there and finished working remotely together. And she built a convolutional neural network to identify flares in the test data. The nice thing is that there were some groups that have hand identified in early test data a large sample of flares. And so we teamed up with them to use that sample as a training set and then train and optimize a neural network to recognize what might be a flare and what might not. This has great benefits because the shape information gives a lot more opportunity for the neural net rather than just a simple outlier cut, especially in fairly noisy test data. Which means that we can recover, especially at the low amplitude end, quite a bit more flares. And so big flares, 10% flares, you see them by eye, no sweat, everyone can find those. But really on the low end, in an injection recovery test, we can see that for the smallest ones, 1-2%, the heuristic-based methods really fail quite a bit. They're at about 10% recoverability, where a neural net can find these at 60, 70%. I see another question here now. I've got it up so I can see them now.
Oh, good. Okay.
Yeah. Hi, Samantha.
Hey, so if we could go back to the last slide, I just have a very basic question, which might have a very simple question, might actually not even matter. But can this neural net actually essentially divine where precisely the flare is, or does the flare have to be centered?
Good question. So we, and actually the next slide is perfect for this. So this is a great lead in. I'll give you the $20 for planting that question later. So we train our neural net specifically to, all the training data we have puts the flare right at the center. And so it learns that a flare is an event at the center of this light curve. And that those are things that are flares. And if we have a flare that's offset, that goes in the training data as not a flare. And so in practice, then we take our data and we take a box. We don't train it. All our training chunks are fairly small chunks. They're 6 hours wide or so. And so then we take a 6 hour wide box and slide it through the data. And at every cadence, ask the neural net, do you think there's a flare here? And so what we get back is something that looks like this, where it slides through and says no flare here. And then when it gets to the middle of the box, it jumps up and says there's a flare here, and then steps down again. And so at the end, we end up with this nice time series of this is where it thinks the flares are, and this is where it thinks the flares aren't. And it's also probabilistic. It gives us back a weighting of, I'm 80%, 60% confident that there's a flare here, which we can use in statistics. Does that answer your question?
Yes, it does. Thank you.
Awesome. Yeah. Well, I've got another one here. Cal.
Yeah. Hi, Ben. Thank you. So you've talked about kind of two extremes-ish of these techniques between heuristic methods and then a full neural network. I was wondering, have you considered, and I'm sure you have, what are the reasons for choosing a neural net over something parametric that might use maximum likelihood to fit a model to these light curves and then use that for flare detection?
Yeah, so we thought about parametric models. The benefit for the neural net is that the Fred profile is okay, but it's not perfect. There are some sorts of kind of quasi-periodic events where you'll see either multiple flares, or they're called sympathetic flares sometimes, of a flare and then another one right afterwards, that affect the shape, and so can cause the parametric models to not actually be a very good fit. We wanted something that we could minimize how much we had to look at it, because there are going to be a lot of data that we didn't want to inspect. We wanted to inspect enough by eye to be confident that it was working, and then not have to look at every light curve by eye to verify. Also, the kind of the reason that we don't necessarily say, but we all agree, is the case that there's a lot of machine learning is a very active thing right now, and so if you write a paper about using machine learning, you can get a lot of citations from that community as well. So that's a little cheeky. We're motivated by the science here of neural nets seem like the most efficient way to go about answering the science goal in the face of we don't have ideal flare models. Having said that, there are better flare models than there were 3 years ago. The group at UW, Seattle, led by Jim Davenport, has really been thinking carefully about how to use the test data to build data-driven models of what flares do and don't do, and they're doing some real impressive work over there.
Great, thanks.
Yeah, and Brian.
Yeah, so just really briefly, just to make things up close and personal. So this is like a 10% flare. At what level do we think they're dangerous? Like if the sun had that, we would be in big trouble.
Yes, we would certainly be in big trouble at this. So there's the famous Carrington event,
right,
from 1859 or so. That apocryphal stories about being able to use telegraphs even if they weren't plugged in. So much aurora down in the Caribbean. That would be in the Kepler bandpass or the TESS bandpass, which are fairly broad, lots of continuum, we wouldn't detect those. That's kind of 0.1%.
Wow. Okay. So these are monsters. Yeah.
So these are huge monsters. Yeah. That's really for a very bright star, kind of best we can do with Kepler, that would be at the limit of detectability.
Got it.
So these are total integrated energy of 2 to 5 orders of magnitude of that.
Wow. Okay.
Yeah.
That's
said that people have used Kepler data because flares seem to follow more or less power law distributions, and so one of the big questions is how common are Carrington events? Should we be worried? Are they 1 in 100 years and we're due, or are they 1 in 10,000 years and we shouldn't worry that much? We don't have the data from the sun to say, but there's lots of sun-like stars in Kepler, and so there's a group led out of Japan by Mehara that's tried to answer this question using the most solar-like stars from Kepler to see how common would Carrington event analogs be. And their best answer is something like 1 in 1,000 or 1,500 years.
Wow. Okay.
For sun-like stars. So enough to keep an eye on.
Cool. To put some perspective. Thanks a lot, Ben. Sorry.
Yeah. And Kale, do you have another question, or is that your hand from earlier?
Sorry, that's all.
Cool. Okay. Very good. Machine learning, awesome. We want to use it. We want other people to use it. So our code is on GitHub. Feel free to use it. It's called Stella because Adina is very good at coming up with clever names that are not acronyms. It's a skill that I don't possess, but good for her. And so for all these stars, we have thousands of stars. We can do really detailed statistics. We have not just flare, not just binary, yes or no, there's a flare, but kind of probabilistic estimates of how likely there is a flare to be here. And we can look at this data over all these young stars from a couple million years to almost 1 billion years and see how they change over time. And not surprising, M dwarfs flare all over the place. They have much larger flares than their more massive stars, which is perhaps bad from a habitability standpoint, both because they have big flares and the planets that are Earth temperature are much closer to their stars. For perspective there's the sun. But one thing that's really interesting about these is that we don't see a relation between flares and the spot phase. So the star is rotating, it's brighter and fainter again. For the sun, flares and spots are highly correlated. When you see more spots, you're more likely to see flares. They come from regions near spots. But it doesn't seem like there is that same relation for these young M dwarfs, for any amplitude flares, the small flares or the big flares. And so why is that? Well, one option is that there is no relation, that there's some different mechanism to where flares can be produced anywhere on the surface of the star. That's a little unsatisfying. But the other alternative is that we're not seeing something like this, where you just have 1 or 2 big spots on the star and nothing else. We're probably seeing something like this, and sorry about the color scheme. We're probably seeing something where spots are all over the star. And so this 4% variability isn't 1%, one side of the star is 4% covered, the other side is 0%. It's probably one side is 50% covered and the other side is 46% covered. And so the variability we're seeing is just extremely spotted to really spotted, rather than somewhat spotted to not spotted. And so if you do the math on what amount of symmetry we see on this spot, what would that imply for how much spot coverage would you need to explain how flat this is? You would need something like 75 or 80% spot coverage. So these stars would be more spots than not spots. But that actually matches a line of evidence from some other work. So Michael Gully-Santiago, postdoc at UT Austin, has looked at near-infrared spectra of young M dwarfs to model their surfaces as multi-temperature components. So a region at one temperature and a region at another temperature, and finding that the cooler the spot region, based off of especially titanium oxide lines, needs to be something like 80% of the surface of the star. And so probably these young stars do actually, from multiple lines of evidence, have something like 80% filling factors. And so when we talk about young stars, we're really telling the stories of spots with a little bit of empty surface. kind of ask yourself, what does it mean to be a spot at that point? Is it, if the whole surface is a spot, is it still a spot? What's the sound of one hand clapping? That's a different conversation. Other thing we see is that sun-like stars don't have regular superflares. The solar bucket down here, bottom center, flares trail off pretty quickly. The young stars, less than 50 million years, have a distribution that looks different from the older stars. And when you break those down more by age, you see kind of the same thing, that they settle down within 100 million years or so. This becomes less and less true the cooler you go, that the faint M dwarfs down here, the very low mass stars, have larger spots and they last for much longer. The distribution over 50 million years does not look really different in a statistical sense from the youngest stars. And so these stars stay active for a really long time, all sorts of problems for their planets. If you build a model of what this might look like for a planet atmosphere based off just the UV flux from these flares, they actually do make a difference in stripping planet atmospheres. That if you build a model of just UV activity from stars, on these young dwarfs, you lose a good fraction of the atmosphere. Over 1 billion years, you only retain 20% of it. But if you add in flares, this is, you lose about 7% more atmosphere. And so it actually really matters to care about flares in this case, to understand what it means to retain an atmosphere for 1 billion years. And so this is something we should be concerned about when we talk about planets around low mass stars. There's so much time and effort going in right now to the atmospheres, and what James Webb will say, what LUVOIR will say, or not LUVOIR, small LUVOIR, in the decadal survey. But what the stars are doing and how that affects the planet atmosphere early on is really something we need to understand more. I see something in the chat, but on the chat open. Will these slides be available? I'll defer to Paul on that one. The recording will be available, I assume.
Yes, the recording will be available on YouTube, but it's up to Ben whether he wants to make the slides available. Sorry to throw it out.
There's nothing proprietary in here, so I'm happy to send, if you want the slides, send me an email later. I'm happy to send you a link. So other point here is that multiband photometry, we assume a temperature for these flares in this modeling. We say something like 9,000 Kelvin, which is a common canonical temperature used based off of solar data. But there's some really cool data from the EveryScope facility at UNC, which is monitoring flare stars simultaneously when TESS is looking at them to get multiband photometry of these flares. With two different band passes, you can then infer a temperature much better than a single band pass. And so Ward Howard was a grad student there, is now just graduated. Looked at a sample of these stars and saw these low mass stars. The flares might actually be something like 40,000 Kelvin, not 9,000 Kelvin. And so the flares can really increase the UVC flux at the top of a planet's atmosphere by something, this should be 10 to 100x, not 100 to 100x. We're not that precise, but it really is at least an order of magnitude and possibly 2 orders of magnitude. So it really makes a huge difference. So one of the things I'm excited about then in the future is using these flares to understand stellar activity cycles. So over 4 years, we talked about the Washington group earlier, this is some of their work. Over 4 years of Kepler, we can see for some stars evidence for the energy distribution of flares changing. Let's skip a couple slides here. We also can see in other data from Kepler, the overall brightness of these stars changing. That sun-like stars can exhibit fairly extreme variability over a few years. We talk about the sun varying by 0.1% in brightness over its 11-year cycle. For some younger sun-like stars, meaning solar temperature, this can be an order of magnitude larger, 1 or 2% variability. And so being able to tie in these brightness variations to changes in star spot amplitudes and changes in flare rates gives us a really nice opportunity in the future to look at activity cycles and how they change. And normally this is done through very, very careful spectroscopic monitoring through surveys like the Mount Wilson survey. That is beautiful work, but it takes a decade or more. If we can get some of this data for free from transit search surveys, we can cut out that waiting. And I'm impatient, so that's good for me. That plot with sun-like stars, but we can see it all over. I'm trying to move my slides back around. There we go. We can see long-term variability on all sorts of stars. This is just a quasi-random sample here of from F stars that probably near the craft break, subgiants, and probably a binary star over there. The brightness can change by a couple % over 4 years. And so tying this into other tracers of magnetic activity really gives us a chance to understand what's going on with these stars. With Kepler, we're limited to a 4-year baseline. Kepler is not observing anymore, unfortunately, but we can be more complete by leveraging other surveys. LSST will fairly soon start observing the sky at multiple bandpasses every couple of nights for a decade, and combining it with TESS, which TESS has plenty of fuel on board. It doesn't use very much fuel at all. The main consumable will be money if nothing breaks. It has enough fuel to last for at least a decade after launch, and possibly as much as 15 years. And so as long as it keeps taking data, we'll get regular chunks of a month of data every couple of years across the whole sky for a decade. And so tying that into long-term variability seen with LSST, if a star is changing by a couple % in brightness over 4 years in Kepler, that's even more changing at the bluer wavelengths probably. And these are not to scale, that's more to scale there. These two together will be really, really powerful for understanding long-term variability, which I'm excited about. Question, Michelle?
So in the graph that you had with the planet atmosphere, was that basically showing that like half the atmosphere would be gone after, I think it said 200, not sure if it was million or billion years? Yeah,
million. It's not a great place. In general, it's not a great place to be around M dwarf early on in its life. That's not necessarily a bad thing. If you still have half your atmosphere, as long as you start with twice the atmosphere you need, you're okay. But there's certainly some stripping. The Earth had some stripping as well early on in its life. But yeah, quite a bit. There's a really extreme variations early on. Young stars are problematic, but also good because the UV, very possibly the high energy radiation that comes with this as well provides some of the chemical reactions, enables some of the chemical reactions that produce life. And so it might be double-edged sword that it destroys your atmosphere, but also without it, you don't get to create life in the first place.
So I guess that's 0.3, not 0.5.
Yeah, but about 2/3. Yeah, it's challenging, but we have very, very good colleagues in astrobiology to think carefully about what works and what doesn't.
Thank you.
Yeah. So test data. This is a little bit of an aside, but I love this slide, and the paper was just published today, so I couldn't not put it in. But in addition to all understanding about stars, test data also provide plenty of surprises. One being we've been thinking of clever ways to try to remove all the stars from test data because we run into solar system objects along the way and other things that are interesting to people. And so these are problems for us sometimes because if a bright asteroid goes through your aperture in front of your star, you get light from your star plus light from your asteroid for a couple hours, and it kind of looks like a flare. So we're interested in seeing where these objects are and what they're doing to our photometry. But other people are interested in the reverse, seeing what these asteroids are doing and getting rid of all the stars. And because TESS is an all-sky survey, it observes, more or less the whole sky, and so we see plenty of solar system objects. And so if you can effectively remove all the stars, you see over a couple of years various objects. So this is there's a jump there. Various objects moving through your sky. This is the so-called mega comet, Bernardinelli-Bernstein. Discovery paper was published today. One of the fun parts of test data of this was that TESS has a very large pixel scale, 20 arc seconds, and an arc minute PSF. And so kind of naturally you would include in your brightness, when you put down an aperture and measure the brightness, your aperture is an arc minute in size. And so if this object has an extended coma, you're going to kind of naturally include that. Where ground-based photometry, if the coma is very diffuse, you might not, so you might model that out in your background. And so when we measured the flux of the star in the test bandpass, it didn't match anything near what, of the star, this comet in the test bandpass, it didn't match anything near what the ground-based data showed, which caused us to go back and really dig into the data, the DES data that discovered it. And we found evidence for extended coma extending 20 or 30 arc seconds. The one we account for makes the photometry line up. So it was evidence that this mega comet was actually outgassing out at 25 AU. It was almost at the orbit of Neptune. And so TESS can provide really useful data for the solar system too. And it just came out today, so I was, I couldn't not show it. On much shorter timescales, turning back to stars, TESS also gives us surprises about seeing how transit signals change pretty quickly. This is some work that led by Elsa Palumbo's a Caltech undergrad working with me through the Caltech SURF program, the REU SAL program. And I've had an exciting morning. I also need to update this because it was accepted today. It says in review on here, but this has been a good day for me. And so Elsa was looking at young stars again in TESS, trying to find planets. And she found this signal in sector 1, kind of funky dip here that looked kind of planet-like. And then as we were trying to understand it, the system was reobserved in sector 27 of TESS 2 years later, and found another dip, which looks similar. It's the same period, which is also the same period as the rotation of the star, which is concerning. But it's also kind of different depth. Something doesn't feel right here. And we looked at the light curve and thought, this is a very, very stable star spot pattern, that this is 2 years of data, 2018 up here, then there's a gap in 2020 down here. This is very, very regular. Star spots are kind of quasi-periodic. They evolve, they come and go. For the sun, they last about 5 rotation periods. But this is something that's regular over a couple hundred rotation periods. And so this is not normal. Maybe it's not spots. You got to think about exotic things. Could this be a black hole where we're seeing Doppler beaming, relativistic beaming of the signal as they orbit each other? We're going to puzzle for a month, and as we were puzzled, this star was observed in one more sector, and the data came out in sector 28. We made a couple of predictions about what we might see, and we didn't expect to see nothing. The transit was completely gone. And there's also this kind of funky, at the end of sector 27, this is the last transit of 27 superimposed on the previous period, this kind of blurb here. So what is going on there? We didn't have a good idea. Thought through what could be causing this. And I thought about some other young stars that are observed by K2 that have kind of similar features. Here's a funky shaped transit from a young star in K2. It's the same deal where it's a little asymmetric. It's co-rotating with the star. It's asymmetric in a way that, in both of these, the long tail points towards the peak rather than the trough. So this kind of felt like it might be the same kind of object, but I didn't really know what it was. So I encouraged Elsa to look at papers too and try to see if she could find something. And she doesn't have the same biases that I have, that I thought we should look at the young star literature. We should look at the low mass stars because this is a young M dwarf. And she went off in places that I would just, discount right away as not relevant for the star. So I found the answer. I think I understand what's going on. She says to me, I found this paper on massive stars. I was like, okay, I don't buy it, but let's tell me your story. And she found this hypothesis called centrifugal breakout that has been used to explain variability of sigma Ori E, especially. It's a model where you have stellar winds that do not have enough kinetic energy to fully escape the star as they get trapped by the magnetic field and clump up in the stellar magnetosphere, and then just kind of sit there for a little bit. And so you see something that is co-rotating with the star, looks like a transit or an eclipse, just clumps right there at co-rotating, continues to accrete mass until it gets so massive the magnetic field can't keep it confined. And so then there's a reconnection event where the magnetic field breaks and lines break and reconnect, expels the material very quickly, and you'd see a flare-like event. So she explained all this to me. It's like, this actually sounds just like what we see, that we see this flare-like event here, and there's a 1-day gap between these two, that we go from kind of as deep as it ever is to nothing within a day. It's like, okay, this seems plausible to me. We did some of the calculations, and it's plausible-ish. So here's the model here, and so with that, but these stars, the stellar wind should be pretty weak. That the kind of scale for what the stellar wind would look like to cause this material to build up wouldn't be amazing. I was then talking about this with a colleague who said, Katja Poppenhager in Potsdam, Germany, who said, I'm working on a postdoc right now who has a model that would fit this perfectly. Which is that for young, active, low-mass stars, CMEs probably don't have enough kinetic energy to escape the star. And so his model is that young stars have coronal mass ejections tied to their flares, and they get trapped in the magnetosphere. And then they collect there. And so if you have an active star with lots of flares, ran Stella through, you can see big flares by eye on the star, but running Stella through for completeness, we see that there's flares all over the place at every phase. And so it seems like this system is an active star where something, potentially CMEs, maybe stellar winds, but potentially CMEs are collecting in the magnetosphere, and then eventually enough material gets built up to where we then, the star's magnetic field can't hold the material anymore, and so it breaks, a little burst where everything comes out, and then the event's entirely gone. This matches what we see. And so it seems to make sense. Where one of the predictions then is that material would fall into the magnetosphere. It would be mostly, hot plasmas. So something that isn't necessarily that deep in broadband photometry would cause the 1% depth that we see in TESS, but something that would be much, much deeper in X-ray data. And so Katja and Julian Alvarado Gomez led an excellent Newton proposal that was accepted to look at the star this year to try to understand what we see. This is the prediction of what we would see under the scenario. It's a 1% deep event in the optical, but something like 50% deep in the X-ray. And so we'll find out hopefully in a few months whether this model holds up. But I'm really excited about where we're going with it. It's also fun. I never put in an X-ray proposal before, and so our exposure, our integrated exposure calculator, calculating what you expect to see. I'm told this is a bright X-ray object. We expect 1 or 2 photons per second. Which it's one of the stories that you hear about, but actually getting to put that in something compared to our 10th magnitude star in the test bandpass that I'm used to as an optical astronomer. It's a fun adventure, and it's a super active star. We talked about machine learning for flares. Not all stars need machine learning. This has a giant triple flare event here, flare, flare, flare over an hour or so. That's so bright. Is shortly after the expelling of the material. It's so bright you can see it in the raw data that this is a GIF, and there's the flare that is in the test data. You can see it. If all flares were like this, we wouldn't need machine learning at all. So the paper was just accepted today. It's on the archive. The newer version will be on the archive in a couple days. It's Elsa's first author paper. But I think this is the first evidence. There's another guy coming around the same time around another star. But these two papers are the first evidence for actual detections of centrifugal breakouts, which is fun for me and it's exciting. It's a model that was developed in the 90s. And they haven't found it because they've been looking at massive stars to try to find it. And we think we've accidentally stumbled across it on low mass stars. Elsa put the whole story together because she went off and wandering through the massive star literature. So there's a story to be said here about getting out of your comfort zone, and from both ends, from the theoretical end and the observational, and thinking about where else your models might be useful, and finding something new to look at to tie the whole story together. I think it made a really, really neat paper at the end that if we didn't look at the massive stars, if Elsa didn't look at the massive stars, we never would have come across. So in the future, just to wrap up here, this is a really golden time for stellar activity, both 25 million stars with TESS. You can find the interesting objects, the one that's telling a wild story that you want to tell, or the large statistical samples of thousands of stars and how that can explain something about habitability. In the future, this is only going to continue. This is the footprint of the Nancy Grace Roman telescope, which will be launched near the end of this coming decade. I really like the footprint. It kind of looks like Space Invaders to me. If you're, I've said this to different crowds, and it doesn't work with undergrads anymore. But for a Colloquium audience, it still works. But one of the things that we'll do is a survey of the galactic bulge for microlensing. But it's a time series photometry mission. It's looking at this field for about a year with a Hubble-sized telescope and a really small pixel scale. And so there's going to be something like 25 million stars again that are observed in this data set. So anything that you saw one of in Kepler, you should see 100 of in this data set. And so anything you didn't see in Kepler because it is too rare, you'll see some of in here within reason. And so this is a really exciting place to go forwards over the next, not this decade, but the following decade for understanding of stellar activity in a very different environment. These are stars in the bulge, and also it'll be sensitive to look at stars in the halo at various points. But for understanding how stellar activity changes across the galaxy, down the galactic metallicity gradients, for stars in different spiral arms, it's really exciting. From a planet standpoint also, I said anything you see once in Kepler, you see 100 of in Roman. That extends to planets too, that the numbers sound a little bonkers, but if you just extrapolate from Kepler planet occurrence, what kind of transiting planets you'd find, it's something like 50,000 transiting planets. Mostly hot Jupiters, but one hot Jupiter is not that interesting these days, but 50,000 of them, you can really tell a story about how planets evolve from there. And of course, then this is a case where once again, hopefully we'll go across 200 years since the discovery of the solar cycle. But once again, we'll have opportunities for planet searches. This microlensing survey, it will be used as a transit survey to tell us about stellar astrophysics. And so the future is bright. There's a lot to be said over the next 20 years. I'm excited about where we're going as a data-rich field and the things we're going to be able to say. So I'm out of time. Thanks all for coming and asking questions and listening. Oh, I didn't mean to do that. There we go. It's been such a pleasure to be here, unfortunately not in person. And I'm happy to take any questions you might have. So thanks.
Thanks a lot, Ben. Do we have any questions? Yes, Sam.
Hi, Ben again. So I do a lot of exoplanetary work, specifically with LSST, and I just had to ask, because I guess I'm a nudge like that. How are you planning on dealing with the LSST's infamously sparse temporal cadence?
Mhm. Yeah, it's going to be interesting for planets. I think it's going to be solvable. I'm glad people are thinking about it. Yeah, it's a big difference going from data every 30 minutes or every 2 minutes to a data point every 3 nights. And for things like separating out planet signals from flares, that's hard. There are some tricks that we can play that are worth playing. One of the things that we see from Kepler is that the PSF is color dependent. And so that's the same for LSST. Flares have a really strong color dependence, right? Flares are very blue relative to stars. And so a planet transit should be achromatic. A flare or a star spot should not be. And so both changes in the PSF and changes in how things look as a function of color, because the multiband photometry will be very helpful, will help us separate out what is a planet from what is the eclipsing binary from what is stellar activity. So I think the LSST will be helped quite a bit from just having 6 bands, all the different color photometry, and weakly from having PSF information. It's going to be hard because there's chromatic aberrations that also happen because of the PSF that are better at high air mass. I think we're the only people saying LSST should go to higher air masses and ignore the zenith. That's not a fight we're going to win, but it'd be great if it did. So I think really the multiband photometry is going to be the best place to go. But it is hard, but it's a problem that has been thought about quite a bit from ground-based surveys. HAT and WASP observe occasionally, every couple nights. And so there is plenty of legacy evidence that these data are really powerful for finding decent planets. And so I think it's absolutely a problem worth pursuing.
Oh, definitely. I completely agree. Thank you for answering my question.
Yeah, absolutely.
Brian.
Yeah, so Ben, thanks so much for your talk. It was great stuff. So and we observers can be really proud of all this great stuff you've done characterizing all these flares. But what's the sort of theory side of things? How what's the status of theoretical understanding of the covering fraction of sunspots, the timescales for the different rates?
It's so active right now on the low mass stars. There's some really cool work from what's his name? His first name is Ben. I remember that, which sounds conceited. It's the group in Colorado. They've been doing really, really cool theoretical modeling of low mass stellar surfaces and are finding these oscillations of the entire upper hemisphere gets covered and the lower hemisphere is pretty sparse, and then it just swaps. And so there's a ton to do from the theoretical side. I don't think we really even understand from first principles how to generate a flare on the sun fully properly, where we have so much data. And so extrapolating to low mass stars is harder. It is very much something that is being led by observations, and people have beautiful, careful stellar models, and then we look at new stars and they don't do what we expect them to do. And so it's certainly there's a lot to be done of understanding how these star spots are coming out and how when you have a fully convective star that changes. There's no tap decline, and so even fundamentally, where is it all just shear from difference or rotation, or is it something else? That's there's kind of the really fundamental questions people are still working on, and so it's an exciting time. But it is a field that's, as my observer bias, it's a field that's a little bit being led from the observational side.
Yeah, very cool. Thanks.
Gil.
So speaking of the observational side, so I work with the South Pole Telescope, and we have some grad students in the astronomy department that have been working on this. I hope they get a chance to talk to you later. We've been seeing a bunch of stars flaring in the millimeter, and some of them are coincident with the optical. Do you have any idea what's going on?
In the millimeter, like at about 1 millimeter, or
Yeah, in 3 bands at 1, 2, and 3 millimeter, roughly speaking. And they're huge, like Jansky flares. Some of them are, like some of them are huge flares.
Not so. That's interesting. I'm on board with that. I'm happy to compare test data on if you have individual objects. Shoot me an email, and maybe there's you get lucky and there's something contemporaneous, but otherwise.
Yeah, we got lucky on one of them. One of them, there's a huge test flare right when Earth goes off.
Great. What's the answer? How big is it?
I don't know. Actually, I don't know if Kadar's on. He was the one that made the plot, but it's huge. It's like that one you said you don't need machine learning.
Well, we certainly see, especially on the very low mass stars and brown dwarfs as well, that the K2 found plenty of evidence of flares that are 10 times as bright as the star on fully convective objects. So the thing gets 1,000 times brighter, 1,000% brighter. And so there's all sorts of extra processing that we go on that. Maybe that material, if it's not exactly simultaneous, maybe it's getting, hitting off a disk and getting re-emitted and at longer wavelengths. If it's a young object that still has circumstellar material, maybe it's just the 40,000 Kelvin black body extends down to a millimeter and is contributing. I'd be interested in exploring the timing and seeing, is it something that makes sense as a few minute delay of, light travel time bouncing off a disk and reflecting at a near infrared wavelength.
Okay.
That could be cool.
All right, we'll have a look. Hopefully you can talk later. We'll see.
Yeah.
Okay, looks like Kadar has posted an archive link you might want to check out.
Yeah, we continuum subtracted it though, but that was a mistake. Well, for the purposes of this conversation.
Yeah, it's exactly coincident with the optical flare.
Yeah,
and lasts for about a couple of hours.
Ben, I'll send you an email. Maybe we could talk next week.
Yeah, let's talk after this for sure. I'll pull up figure 6 real fast, and we'll look at it here. But yeah, shoot me an email. I'm very happy to talk later.
I'll try to track you down.
Yeah, I'm. Oh yeah, look at that. That's cool. Yeah, I haven't seen this paper. Let's. I'll take a peek and let's talk later. It seems neat.
Great. We need help.
Yeah, we're always happy to consult.
Thanks.
Ben, I'm curious as the implication of these very large flares for gyrochronology. There's this Schumanich law that main sequence stars have a rotation rate that slows down with time, and that comes from magnetic coupling to their winds. But for these large flares and low mass stars, do they, does it change that relation? Does it make it more episodic? Does it have any effect at all?
Yeah, that's a great question. And it's one where, see, I don't have a slide on here, but I have a slide from another presentation with me as a backup. I think we don't have the data to say at this point, is the short answer. There is certainly lots of evidence. Am I going to pull it out? I might not be able to. I don't have the slide, but there's lots of evidence that are kind of simple gyrochronology relations that are built over a few clusters are not as easy and convenient as we want them to be. Here's the figure I want. And so this is kind of 3 youngish moving groups, Pleiades, Persepi, and NGC 6811. So let's look at the left panel here for a second. And we can see that the story isn't as neat as we want. First off, the M dwarfs don't slow down over the first billion years. They're always at a couple day rotation periods. As things are the scales kind of work from left to right better in time. But there are pauses that the 670 million year and the billion year clusters are right on top of each other for K dwarfs, but not for G stars. And it seems like there's some evidence that the sun might be in a transitional phase as well. And so the lie we tell ourselves about here's a power law that gives you the age of the system based off its color and rotation period. At young ages, it is definitely more complicated than that. That things move very quickly from 100 million to 600 million years old, as much as things can move quickly over 500 million years, and then they stop for about that amount of time as well. And there's probably also effects of metallicity that will change the way the stellar winds behave that are explicitly not included in the models. And so the answer is almost certainly yes, but we don't have the data right now to deeply understand how that works. But hopefully over the next several years, as we get more observations of young moving groups in TESS, more measurements of rotation periods, and also observations of stars at different metallicities, this is something that we'll go for. Another thing I'm excited about is wide binaries, stars where you have co-moving from Gaia, an evolved star, so its age extremely well, with some binary main sequence companion. Now you're really cooking, and so we can understand over a much broader range than limiting ourselves to the clusters, all at whatever metallicity they have.
Yeah, cool. Thank you. One more question, Chris.
Hey, Ben, great talk. I'm one of the grad students working with the flare stars on SPT stuff. And I use Eleanor a lot. It's fantastic. Great job with that. How do you, so this chart here with the rotation period, you have a little bit going above 15 days, but how do you know there's not any longer rotation periods with the test data, and how far up does your data actually go?
Yeah, good. So for those who don't know, Eleanor was another project led by Adina here. It was her first year PhD project, was building a software tool to make light curves from all of the TESS full frame images. And so it's public software anyone can use, and hopefully with 2 lines of code, make a light curve for their favorite test object. And so if there's something in TESS you're interested in, check it out. I think it's easy to use. I like it. Yeah, question here, TESS has kind of 27 days of data at a time. So how do we get longer rotation periods? It is a challenge. NGC 6811 here is a cheat because it's in the Kepler field. And so that's when we're at 4 years of data. But in general, yeah, things get hard when you get to the baseline of your observing. This is part of the reason why we want these kind of longer baselines. We want to revisit these fields over and over to get more data. The continuous viewing zones are helpful because there you have a year of data. There's still a struggle of you have an offset every month because your star is landing on a different pixel with different systematics, different underlying things going on. But we're working on it. One of the things that I'm excited about, I actually have a backup slide here, I hope. Why would I delete that slide rather than just, that was a mistake. All right, one of the things we're playing with, here we go, is looking at really, really long rotation periods and how can we do better at not removing those in TESS and Kepler data. And one of the ways we're going for this is Psf modeling, where if you're worried about your aperture effects and pixel level effects, if you can model the point spread function of the star, you can do a better job at understanding how it's moving in and out of the aperture, and any long-term systematics over a month of Kepler, you can do a better, or a month of TESS, you can do a better job mitigating. And so this is an example of a star where this is after it's run through the Kepler pipeline. which tries to remove long-term effects, anything longer than about 40 or 50 days, because they're just overwhelmed by systematics. And doing a careful PSF model and trying to incorporate how much of the star is in your field of view and how much is not, and putting in every correction we can, we get a light curve that looks like this, which has about 100-day rotation period, about 120 days. And so I think there are tricks that we can play for doing better in the data processing. I think it is a data processing problem rather than a telescope limitation, to get things that are similar to your baseline. You can imagine Kepler takes 90-day quarters at a time. You can imagine just taking 90-day chunks of this, you get a piece of a rotation period. And if you get it a couple years apart over and over, you can then still make a pretty strong inference as to what the rotation period looks like. Analogous to Sam's question about getting inferences about a shorter period planet with sparse data. And so I think there is opportunity there. And part of it is better data analysis methods, and part of it is just waiting and having not 27 days of data, but 27 days of data 5 times over 6 years will really help us.
That's great. Thank you.
Yeah.
Okay, well, I think we're getting toward 5 o'clock here, so why don't we thank Ben again. I wish we could have had you in person, but perhaps someday.
Yeah, next time.
Yeah, it was a great talk. Really enjoyed it.
Thanks for having me. So my pleasure.
Thank you.